Good evening, everyone. I am Anayesh Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. This is the PMRF interaction for the week 12 lecture for the NPTEL course Solid Mechanics. This course is being offered by Professor Ajit Kumar from IIT Delhi. In this week, Professor Ajit Kumar covered concepts of different failure theories and how do we apply them in practice. The first problem that we have is as follows. When using the maximum shear stress theory of failure, we compare the maximum shear stress in the body with. So the shear. Do you know the answer to this?
No, sir.
Okay. So the maximum shear stress theory. Uh,
No, I
it basically says that this if lambda 1, lambda 2, and lambda 3 are your principal stresses. These are your principal stresses. Then from Moore's circle, like for the 3D case, we know that your tau max is essentially mod of sigma 1 minus sigma 3 by 2, where I'm writing sigma 1 greater or equal to sigma 2 greater or equal to sigma 3, like in descending order. Then your maximum shear stress theory is basically written as norm of lambda 1 minus lambda 3 by 2, which is tau max, is should be less or equal to sigma y by 2. So this basically is the option B.
Sir, what is sigma y?
Sigma y is the yield stress and tension. So basically what happens is, suppose we consider a beam or a rod like this, okay? Consider a beam and I'm applying some force F on it. Let the beam have some cross section area A. Now what I can do is I can calculate my sigma xx. So this is under say uniaxial tension, which would mean that the body experiences force only along the length of the body, which I'm drawing to be x-axis, and it also elongates only along the x-axis. So in the uniaxial tension test, what we do is we check how the body's normal stress is related to the normal strain. And when we do this plot, we initially see it to be a linear plot. This is the basis for your linear stress strain relations that you have learned in previous classes. This is the experimental basis. And then after a particular point, this, sorry, yeah, after a particular point, which I'm calling as epsilon L, marking the limit of linear strain, this whole thing becomes non-linear and it reaches a point uh, called as the yield stress sigma y. What happens is basically till this yield stress point, if you release the body from any of these x marks, if you basically stress the body under uniaxial tension up to any of these x marks and then release it, the body will go back to origin, which is the zero strain condition, zero strain, zero stress condition. But beyond this yield point, you have a different behavior. If I leave this body back from the circular mark, it will return to a different point where sigma will become zero since it's under no stress, but the body is now permanently deformed. This is called as your plastic strain, epsilon p. So sigma yield stress is basically the maximum stress up till which you can basically apply stress on the body, and when that applied stress is removed, then your body will recover back to its original geometry, to its original shape. If we go beyond the yield stress, you will have a permanent deformation in the body, which is what we call as failure. Is that clear?
Yes, sir.
Okay, good. Let's look at problem number two. It's a simple true or false statement. The given statement is the maximum normal strain theory of failure can be applied even when some shear strain is present in the body. Do you know the answer to this? So I'll just write down our epsilon xx tau xy
No, sir, I don't.
tau xy. Suppose I'm writing those in this particular state of stress. Okay. As you can see, for the uniaxial case, the body only had epsilon xx, but because of some reason in this particular case, you may also have say tau xy, which is what the statement is saying. And then it is asking us, can we still apply maximum normal strain theory? So what we do here is similar to the way you have principal stresses sigma 1, sigma 2, sigma 3, which are eigenvalues of the sigma stress stress tensor represented in matrix form. You similarly have, these are your principal stress. So if you rotate your coordinate system to a particular, so that it aligns to your principal stresses, your sigma essentially would in that coordinate system would become lambda 1, lambda 2, lambda 3, a simple diagonal matrix. So for the case of uniaxial stress, you could have like sigma 0, your sigma would be sigma applied 0 0 0 0 0 0 0 0. So you can see that this is essentially of the same form as this, and hence you can directly look at lambda 1, lambda 2, lambda 3. So here lambda 1 is sigma, lambda 2, lambda 3 are set to 0. Something similar happens in the case of strain tensor. So a general strain tensor can be written as epsilon xx, epsilon yy, epsilon zz, gamma xy, sorry, epsilon xy, epsilon xz, epsilon yx, epsilon yz, epsilon zx, epsilon zy. This is how a general stress tensor for a particular coordinate frame xyz can be written as. What I am now saying is we do basically a rotation of coordinate system to end up with x1, y1 and z1. In this particular coordinate system, you can write your epsilon x1, y1, z1 as epsilon 1, epsilon 2, epsilon 3, a simple diagonal matrix. How do we find the entries of diagonal matrix? We basically take this and find its eigenvalues. So once you have found the eigenvalues, you have epsilon 1, epsilon 2 and epsilon 3, and you want to compare this with the maximum possible, uh, since it's the maximum normal strain theory. What we have is, in this rotated frame x1, y1, z1, you only have normal strains epsilon 1, epsilon 2, epsilon 3. So now you compare each of this with the maximum possible strain. That is essentially your maximum normal strain theory. Okay, so we can
I
do
am
this.
sorry, but
Huh, go on.
sir, can you explain maximum normal strain theory? In the quote, Ajit Kumar sir has not mentioned that.
It's, in a sense, it is similar to, so in wait So how do we write maximum normal stress, right? Maximum normal stress theory is written as max of sigma I, where sigma I is the principal stress. This should be less than or equal to sigma Y. The same way you can write maximum normal strain theory. Max of epsilon I. So the maximum normal strain theory can be applied even when you have some shear strain, because we'll be solving the eigenvalue problem, then moving to the rotated frame where there are only principal strains, which are only normal strains and no shear strains.
Okay.
Okay. Problem number 3. The total strain energy for isotropic materials is given by general deformation of the body can be thought of as volumetric strain, which is essentially your uniform contraction or expansion, plus distortion strain. So this basically means that you can write your epsilon is equal to 1 by 3 trace of epsilon I plus epsilon minus 1 by 3 trace of epsilon into I. So we are decomposing our epsilon matrix or our strain matrix into two terms. First one is a diagonal matrix which has the terms epsilon 1 plus epsilon xx plus epsilon yy plus epsilon zz by 3 times 1 0 0 0 1 0 0 0 1. So this term is, you can think of this, right? It's a uniform contraction or a uniform expansion. If epsilon xx plus epsilon yy plus epsilon zz is positive, then your entire cube would uniformly expand. So this is basically your volumetric strain, and the other term is your deviatory stress or strain. I'm interchanging it with distortion term. So this the first term would look something like every part of the cube is pulled with the same way, whereas the second term would look like you have some different pulls in different directions. So the cube might the cube might be flattened in one direction and expanded in another. The cube might also shear in different directions as shown by these arrows. So say since your general deformation is in that manner, your total strain energy is also decomposed in a similar manner. You have a volumetric strain energy term and a distortion strain energy term. This is specific, yeah, this is specifically true for isotropic material. You can write it down also as SE total is half sigma ij epsilon ij summation over I and summation over j, and your SE volume is half sigma volume epsilon volume, where sigma volume is nothing but sigma 1 plus sigma xx plus sigma yy plus zz by 3, and this is nothing but epsilon volume is 1 1 plus epsilon x plus epsilon yy plus epsilon zz by 3, and you get these epsilon x, epsilon y, and epsilon z terms from Hooke's law. which is nothing but 1 by E times sigma xx minus nu times sigma yy plus sigma zz. Okay, so your total strain energy, this is your volumetric strain energy, and your distortion strain energy is nothing but the difference of these two. Okay, so this basically gives you the expression to calculate total energy and volumetric strain energy. Is this is this clear?
Yes, sir.
Okay. The fourth problem. For a deformation problem, suppose the stress matrix is represented in E1, E2, E3 coordinate frame, where E3 is the principal axis. So let us look at sigma. This is sigma xx or sigma. We have 1, 2, 3, right? So I'll use that. So you have sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2, sigma 3, 3. It is given that E3 is a principal axis. So you would essentially have zeros here because on the plane which is normal to the principal axis, you only have normal stress. You do not have shear stresses. This is the stress matrix that we are given in general
I'm
form.
sorry, sir, but can you,
Go on.
sir, will you explain it once again? Can't able to catch.
Okay. Okay, we'll first look at the first statement. So the first statement is this is a deformation problem and the stress matrix is given in the E1, E2, E3 coordinate frame. Okay, so you've got E1, E2 and E3. A general stress matrix in this frame would look like sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. Now we know that the diagonal terms are normal stresses and sigma ij would essentially mean that it's the it's the force it's the force I and on the jth plane. So if we look at the first column, sigma 11, sigma 21 and sigma 31, these are all the forces that you would get in the body. Suppose this is my body, this is direction E1. So if I cut a plane whose normal is E1, right? And now I look at this plane, I would have different forces on it, right? My overall force may act in a oblique direction to the normal. Now if I decompose this oblique force, what I get is basically three different force components. And now as I shrink down this area, so here I should put limit of Ag tends to 0. As I shrink down this area to a smaller and smaller area around the point, what I'm left is ratio of the force with the area. That is essentially what we are writing in our matrix components. So this component would be sigma 1 1. This component is along 2, but direction of that force is along 2, but it's on the plane with normal along 1, and this component coming out of the plane would be sigma 3 1. Okay, now we are
So,
told that E3 is the principal axis. So since E3 is a principal axis, so that is the first condition that we require to actually use Moore's circle. You need at least one of the coordinate axes, E1, E2, E3, to be a principal axis. And as soon as you have a principal axis, so if you remember, we did this here. As soon as you have a principal axis, your general state of stress or a general state of strain will be transformed to a simply a diagonal matrix. For stress, it would be a diagonal matrix like this: lambda 1, lambda 2, lambda 3. Okay, this
Okay,
also
sir.
essentially means that there are no shear terms. This term is 0, this term is 0, right? So as we observed in our this diagram, this term is, say, the sigma 2 1, this term is sigma 3 1, right? Once you go on to your principal axis, your shear terms are becoming 0. Your normal term is non-zero. Your shear terms are necessarily 0 rather. So
Okay.
we are given that E3 is the principal axis, which would mean that sigma 1 3 is 0, sigma 2 3 is 0, sigma 3 2 is 0, and sigma 3 1 is also 0. This is because from angular momentum balance, we know that sigma 3 1 is equal to sigma 1 3, sigma 3 2 is equal to sigma 2 3. From angular momentum balance, sigma ij is equal to sigma ji, which essentially means that this entire matrix is equal to its own transpose, and therefore this matrix is symmetric. We established that E3 is the principal axis, so sigma 3 3 can be non-zero, but these two are necessarily 0, and since this matrix is symmetric from angular momentum balance, sigma 3 1 and sigma 3 2 must be 0. With this in mind, our matrix essentially becomes sigma 1 1, sigma 2 1 0, sigma 1 2, sigma 2 2 0, 0 0, sigma 3 3. Next thing we are told is a Mohr circle is drawn. So a Mohr circle is drawn for this particular state of stress. Mohr circles is drawn. So you have sigma and tau. Tau is the shear stress. I should write this as tau rather. Tau is the correct notation. Tau 1 2 and tau 2 1. And suppose this is, so we basically locate these points sigma 1 1 sigma 1 1 tau 2 1 on this plane, and sigma 2 2 tau 1 2 on this plane. So one point might be here, another point might be here. And the center of the circle, we know it is average of the two normal stresses. So center point is equal to sigma 1 1 plus sigma 2 2 by 2 comma 0. So we know the center point, and we know that this particular point is the sigma 1 1 comma tau 2 1. We know the center, we know this point, we know it's a circle. So we can just draw this
Sir, then
circle.
why we should not, sir,
Huh? Yes. Go
sir,
on.
why we are not 3 3 on the Mohr circle? 3.
Okay. Uh, 1 second. I'm trying to remember. Okay. You have. Okay. I think it's a slightly involved explanation, but I'll try my best. Suppose this is your cube and this is your E3 direction, right? Same coordinate system I'm using here. You would have something like sigma 2 2, tau 1 2, sigma 1 1, tau 2 1. This is sigma 3 3, right? Once you have this state, once you have this kind of a state of stress, which is what we are given here, I can again, I'm using the above equations only. So you have sigma 1 1, sigma 1 2, sorry, tau 1 2, and you have tau 2 1 0, sigma tau 1 2, sigma 2 2 0, tau 1 to sigma 2 to 0 and 0 0 sigma 3 3, right? Now
Yes, sir.
Mohr circle is basically that suppose we rotate this cuboid and we want to look at this particular kind of a cuboid. Okay, the normal is still sigma 3 3, but the E1 is now rotated to E1 dash by angle theta. E2 dash is again at an angle theta with E2. Okay, this sort of rotation. Sorry. For this particular, for if I rotate it, if I rotate it, if I look at this plane, which is the E1 plane, and now I want to look at, so in E1 plane our traction was T1 is equal to sigma into E1, but E1 is nothing but 100. So you would end up with the first column. Okay, this is the traction on the E1 plane. Now we want to calculate the traction on E1 dash plane. That would be T1 dash is equal to sigma times E1 dash. This this would essentially be, so you would have a cos theta sin theta 0. If I write it this way, you end up with sigma 1 1 cos, uh, you would end up with something like sigma 1 1 cos theta plus tau 1 2 sin theta, then tau 2 1 cos theta plus sigma 2 2 sin theta, and the third term is again 0. With this particular traction, if I now want to calculate the normal sigma 1 dash, it would be T1 dash dot E1 dash, and I get some relation which would essentially be sigma 1 1 plus sigma 2 2 by 2 plus sigma 1 1 minus sigma 2 2 by 2 cos square cos of 2 theta plus tau x sine of 2 theta. This is what I get for like the normal force on normal stress on the E1 plane. So once I have rotated it like this, the cuboid is rotated like this. This component that I am getting is sigma 1 dash sigma 1 dash. I should write 1 dash 1 dash. And then you have a shear component tau 2 dash 1 dash. I can similarly do a relation here from this traction. I can subtract the normal stress because the overall traction would look something like this. I can subtract the normal stress from this traction T1 dash and get the shear stress. And then I again get some equation that would look like tau 2 1 dash is equal to minus of sigma 1 1 minus sigma 2 2 by 2 sine 2 alpha sine 2 theta, yeah, 2 theta plus tau 1 2 times cos of 2 theta. Now if you look at equation 1, and this is equation 1 and the top one is equation 2. Now if you look at these two equations, you can right away see that there is something interesting happening here. You have a, say like a cos theta plus b sin theta and minus a sin theta plus b cos theta. If I now combine these two equations, what I see that this is essentially the equation of a circle with this is essentially an equation of a circle where my normal stress would be sigma 1 1 plus sigma 2 2 by 2 plus r cos say some beta, and tau is equal to say r sine of beta. Now this radius is basically root of a square plus b square, which is sigma 1 1 minus sigma 2 2 by 2 whole square plus tau 1 2 whole square. And this beta is calculated, beta is basically 2 phi minus 2 theta, where phi is the original phi is the original deviation of the point. So what I mean by this is, once I have this condition, right, that E3 is basically a principal axis, I am able to see that for any transformation, for any rotational transformation by some angle theta with respect to E1 or E2, I am directly able to obtain the normal stress on that plane as well as the shear stress on that plane. This is the basic idea behind Moore's circle, and it gives you something like this. Your radius is sigma 1 1 plus sigma, your center is sigma 1 1 plus sigma 2 2 by 2. You have some radius, and your points are sigma 1 1 comma tau 2 1, and another point would be sigma 2 2 comma minus tau 1 2. This angle is basically your 2 phi, the angle you begin with initially. With this is the reason why Morse. So with to summarize, with Morse circle, you can easily calculate the normal stress and the shear stress on any plane. You can rotate this theta, have it at 5 degree, have it at 105 degree, have it at 245 degree or 310 degree. You can still simply use your Morse circle and determine sigma and tau on that particular plane. It's a very easy method, but it requires that your sigma 33 must be aligned along, sorry, your E3 must be aligned along one of the principal axes, which is what is given in this problem as well.
Okay, sir.
Sorry, that was a bit involved, but I didn't know how else to go about it. And once you have your Morse circle, right, this Morse circle will intersect on certain points on the x-axis. And if you look at these points of intersection on your x-axis, you can observe that on this particular point there is no shear stress, right? For point A and point B, you have no shear stress. I'll name them as
Okay.
lambda 1 and lambda 2. These are essentially again your principal stresses. So Morse circle also gives you principal stresses directly. And we are given that the principal stress components are basically 10 Pascal and 20 Pascal. So I'll write somewhere. I'll remove a bit of this. So now that I have this Morse circle, I have basically got lambda 1 is equal to 10 Pascal, lambda 2 is equal to 20 Pascal. And the normal stress along the E3 axis, that is something we are not given. So lambda 3 is unknown. Okay, lambda 3 is basically sigma 33 and it is unknown. And then we are told that sigma y is equal to 25 Pascal, right? And we are also told that we want to apply maximum principal stress theory. Maximum principal stress theory. So that is nothing but your max of lambda I should be less or equal to sigma y. This is your maximum principal stress theory, correct?
Yes, sir.
Now we know that out of lambda 1 and lambda 2, your maximum is 20 Pascal. 20 Pascal is definitely less than 25
Okay.
Pascal, but we do not know the value of lambda 3. Suppose lambda 3 is again 20 Pascal, we are okay. If it's 15, it's okay. But if it's 30, then the maximum of lambda would be 30, right? And since 30
Okay.
is greater than 25, then the body would fail. So our answer should answer must depend on if we have the whatever the value of lambda 3 is, whatever the value of sigma 3 is, right?
Yes, sir.
So which option is there? The failure of the body would depend on the value of the third principal stress component, which is nothing but lambda 3 or sigma 3. Problem number 5. Suppose we want to design a body of some material which has a yield stress in tension of 10 pascal. So we are given sigma y is 10 pascal. We are also given that the factor of safety should be 2. So n is equal to 2. And we are told that we should consider the maximum principal stress theory of failure. Which of the following must be true? Okay, so maximum principal stress theory again. Max of lambda I should be less or equal to lambda sigma y. Correct? But we are given that some factor of safety has to be used, right? So this
Yes, sir.
would basically modify with safety factor, and this would basically, we can basically rewrite this as maximum of lambda I n times maximum of lambda I should be less or equal to sigma y, which is nothing but max of lambda I is less or equal to sigma y by n. I substitute the values, that is 10 by 2, which is 5. So your maximum principal stress component should be less than 5 Pascal, which is
Mm.
which is the last option. Yes,
No, sir.
got it. Okay. Problem number 6. The distortional energy in a body is proportional to. Okay. So we know that SE total is half summation I summation j, half of sigma ij epsilon ij, and we know that your SE volume is half sigma volume epsilon volume. Your SE distortion would be basically the difference of these two. Once you work this out by plugging in your hook, sigma xx is 1 by e times, sorry, epsilon xx is 1 by e times sigma xx minus mu times sigma yy plus sigma zz. Once you plug this into here and also in here with sigma v and epsilon sigma v as basically as volume average, then you get an expression for distortion energy which would look something like times in I'm writing this in terms of principal stresses, minus of sigma 1 sigma 2 sigma 2 sigma 3 plus sigma 1 sigma 3. So this is how your distortional strain energy would look like, strain energy density would look like. I think Professor Ajit has covered this in the lecture, right? Second
Yes,
last
sir.
lecture, right? He has covered this derivation, so I'll not.
Yes,
So you could also refer to that if you want the derivation here. And okay, so it is clearly not proportional to the volumetric strain energy, right? Neither is it proportional to the square of volumetric strain energy density. And the next two options involve octahedral shear stress. Uh, So do you know, or do you want me to go through octahedral shear stress, or do you know what it is?
yes, sir.
Okay. Sorry, you know, or you want me to go?
I want you to explain it, sir.
Okay, okay, got it. So, So what we have is basically E1, E2, E3, right? These are your these these are your principal normals, and what we are looking at is a plane like this. Okay, we are looking at a plane, and which is basically equally composed of E1, E2, and E3, which is an equal sum of E1, E2, and E3. If I want to write, I can write it as 1 by root 3 times E1 plus E2 plus E3. And if I want to write it in vector form, it would be 1 by root 3, 1 by root 3, 1 by root 3. This is one of your octahedral planes. You could basically do a plus minus on all these 1 by root 3's, and you could end up with 2 into 2 into 2. So you could have a total of 8 octahedral planes. So the way another plane say would look something like this, then another plane would look something like this. Then you could have one more plane from this point, and this point, and then you can extend even in the negative direction, 1, 2, and this point. It basically would look something like, my drawing is not particularly good, but it would look something like this. So this direction coming out is say your E3, this is your E1, this is your E2, and this whole system is also in the opposite direction. Okay, so these are your 8 octahedral planes. Again, octa is there itself in the word, and you want to look at what happens to the shear stress, and you want to look at both the shear and normal stresses here. Okay, so if you remember, traction on a plane is nothing but sigma into n, where n is the plane normal, and this you can rewrite as sigma n, sigma norm. This is the normal component, and this is your shear component. Okay, I'm basically decomposing our traction on any plane into a normal component. If my traction Tn looks like this, I'm decomposing it as sigma n and tau. Okay, and I now know my n value, so I can just go ahead and plug it in to get Tn is nothing but, I'm showing this case, I'm doing this for the case where E1, E2, E3 are principal axis, but you you could find, but what you'll find out once we go through the result is that they are basically, it doesn't matter like what axis you take up with, because your normal and shear stress values end up coming out as, sorry, come out essentially as a function of the stress invariant. So the invariants, by their name, suggest that they do not change with the rotation of the frame. Like, you can move around say you can move your entire frame to a particularly different axis as E1 dash, E2 dash, and E3 dash, and whatever your stress component may change, your stress component will change rather, but the stress invariants won't change. I'll just go through this for the principal axis case because it's simpler to derive it here. And as you can see, your Tn would look something like lambda 1 by root 3, lambda 2 by root 3, lambda 3 by root 3. Now if I want to calculate the normal component, it is nothing but Tn dot n. So Tn dot n would give you the normal component sigma, which is nothing but lambda 1 into 1 by 3 plus lambda 2 into 1 by 3 plus lambda 3 into 1 by 3. Okay, you can do a dot product here, right? This vector dot this vector, 1 by root 3, 1 by root 3, 1 by root 3. So first term would be lambda 1 by root 3 into 1 by root 3, which is lambda 1 by 3, plus the second term would be lambda 2 by root 3 into 1 by root 3, which is lambda 2 by 3, and the third term would be again lambda 3 by, similarly would be lambda 3 by 3. So this gives us our normal component. So this would be our octahedral normal component. And this is also the first stress invariant, 1 by 3 times I1 of sigma, which is nothing but 1 by 3 times trace of our sigma matrix, trace of a general sigma matrix. So here it is diagonal, but in general it can be, as we saw earlier, it can be lambda sigma xx plus sigma xx sigma yy tau xy tau xz. Okay, so this invariant part, which is the trace here, is remains unchanged even after rotation of the frame. Now we have obtained the octahedral normal stress. We want the shear stress. So the magnitude of the normal stress plus magnitude of the shear stress should be equal to the magnitude of the traction. Correct? From Pythagoras theorem. This square plus this square equal to this square. And we know Tn, we know sigma n. You can see where we are going here. So tau n square is nothing but Tn square. Norm of Tn square. So norm of Tn square would look like, since it's a vector and we are taking the square of norm, we'll basically be adding each component. So you would have something like lambda 1 square plus lambda 2 square, lambda 1 square by 3 plus lambda 2 square by 3 plus lambda 3 square by 3. This is my Tn square minus sigma n square. Sigma n would be lambda 1 plus lambda 2 plus lambda 3 by 3 whole square. Right? I take this 1 by 3 whole square would be basically 1 by 9. I'll remove 1 by 9 and I get 3 lambda 1 square plus 3 lambda 2 square plus 3 lambda 3 square minus this whole square, lambda 1 plus lambda 2 plus lambda 3 whole square. If I expand it, it would be lambda 1 square plus lambda 2 square plus lambda 3 square plus 2 lambda 1 lambda 2 plus 2 lambda 2 lambda 3 plus twice of lambda 3 lambda 1. Correct? And if I just
Yes, sir.
get this all terms together, I have basically 2 lambda 1 square plus 2 lambda 2 square plus 2 lambda 3 square minus twice of lambda 1 lambda 2 minus twice of lambda 2 lambda 3 minus twice of lambda 3 lambda 1. I'll take the 2 outside for convenience, and I end up with lambda 1 square plus lambda 2 square plus lambda 3 square minus lambda 1 lambda 2 minus lambda 2 lambda 3 minus lambda 3 lambda 1. And this is tau n square. Compare this with this, and you can quickly see that it's
Yes,
basically
sir.
uh
Octahedral shear stress is the answer.
yes, the tau n square is proportional to AC distortion. Problem number 6 is done. Problem number 7. Consider two beams made of identical material and having same geometrical dimension. So I'll just draw them here. This is my beam 1, this is my beam 2. I'll also draw a coordinate axis x, y and z, and both are subjected to the same axial load. So P and P, but beam 2 is also subjected to a change in temperature of T. Okay, I'll write it heat by T. And we are asked which of the following holds true, assuming the beam's axis lie along the x-axis, which is what I have drawn already, and alpha represents the coefficient of thermal expansion. So if t is 0 essentially, you would have epsilon xx1 is equal, if t is 0, epsilon xx1 is nothing but epsilon xx2, correct, right? Because it's the same beam, same material, same geometry, same loading, everything is same mechanically, materially and geometrically. Now we are
Yes,
told that t is non-zero. What this would do is this will cause a volumetric expansion in beam 2. So all the line segments in beam 2, so all line segments in beam 2 expand.
sir, the answer is the first option.
Yeah,
It
it
is
it
alpha t.
expands by alpha t, right? So your
Yes,
epsilon xx2 would be greater than your epsilon xx1 by a factor of alpha t, right? So which is the answer? It's the second one. It's the other way around. Epsilon xx1 is equal to epsilon xx2 minus alpha t. This body 2 is under heat, right? So option B. Okay.
did one. The I am confusing between the option one and option two.
Oh, option 1 is essentially epsilon xx1 is epsilon xx. Option A, I'll write. Option A is epsilon xx1 is epsilon xx2 plus alpha t. So this is basically saying that beam 1 expands same as beam 2 plus an additional due to the thermal one, plus additional expansion due to thermal, which is not right, as it is the beam 2 which is undergoing thermal expansion, not beam 1, right?
Yes, sir. Yes, sir. Okay. I got it.
Okay, problem number 8. Consider a thermoelastic body. We do not apply any loading but increase the temperature by T. So no loading. This is my body, or I can draw it like this also, it doesn't matter. This is my x, y and z coordinate frame, and I'm upheaved by T. Right, this is the same thing, and we are asked which of the following is true. So as we discussed in the earlier example, heating only causes, so if you heat, only x only strain for line segments. So you would have your epsilon xx, epsilon yy, epsilon zz to be equal to alpha t, right? This is what heating would do, but there is no mechanical loading here, right? The body is not constrained with either by clamping or any other boundary condition here, right? So this body will simply expand, and if it's simply expanding without any bounds, there is no internal forces being generated here.
Okay. So normal stress will be zero and shear stress will also be zero.
Yes, both will be zero, correct. Problem number 9 is a true false statement. The stress strain curve continues beyond the yield point for ductile material. This is what we saw in the first. If you remember, I talked about a body like this
Yes, sir.
with force, and I'm seeing how this body behaves. And we talked about a point of linearity, then the yield point Ly. After that, it undergoes something called as necking at UTS, and it finally breaks here. This is for the ductile body.
Yes, sir.
For brittle bodies, it doesn't even go. So it would go say something like this and break here itself. So there is no this flattening that you observe in ductile case, right? You do not observe it for the brittle case.
What is flattening, sir?
Flattening is essentially that for no change in force, it is also called as plastic flow. So have you ever pulled Have you ever pulled like a plastic wrapper or a have you ever done this by hand? You have a polythene bag or something like that, and we pull it, right? So if you pull it a little bit and leave it, then the plastic bag would go back to its original shape. But suppose you keep on pulling it, there comes a particular point where it seems as though like for the same amount of force that you are applying with your hands, right? The plastic just keeps on expanding. Have you seen this happen ever?
Yes, sir. So flattening means that
Without increase in sigma.
without increasing stress, there will increase in strain.
Yes. That is actually the very definition of what ductility is. So in ductility, if you look at ductility is the ability to be drawn into thin wires. This is what metals have. Like once you pull them beyond even beyond that particular point, they'll just roll out into this thin wires, which is what makes them, which along with their conductivity properties also make them suitable to your
So the
electrical.
answer is true, sir.
It's
Right.
true. Yes, brittle materials will just break. Brittle are they'll expand to a particular point and then they'll just break like a chalk. Have you ever tried this? A chalk is a brittle material. A glass is also a brittle material.
Yes,
So
sir.
yeah. Okay, the last problem for the day. A beam is clamped at both ends. So this is our beam. We'll clamp it at both ends, and then we'll heat it. So again, heat by T. Again, they are told the same thing. Assume axis along X, Y, and Z. And we are asked which of the following holds true. Okay, do you want to try this? What what will happen if there are no clamps? Okay, or if there is suppose only clamp on one end and you heat it, what will happen? If there are no clamps, right? Body is like this, and you heat it, what will happen? It will just expand, right?
Yes, sir. Yes, sir.
And
Here, as it has clamps, it will induce compressive stress.
yes, it will try to expand, our body will try to expand, but unfortunately it cannot because of the clamping. Therefore, a compressive stress will be induced to basically hold the body in its place.
Yes, sir.
Okay, and so the axial load will be compressive. It won't be tensile. Obviously, there is since it's clamped, it will be induced. So this is wrong. This is also wrong. Oh, and the final option. Do you think will there be any shear force in the beam?
No, sir.
Yeah, correct. So yeah, this brings to an end to the problems that I had for failure theories week. Do you have any other questions?
Sir, will you explain a sample problem on distorted energy theorem? Distorted energy theorem of failure, if possible.
Sample problem. Okay. Okay. Suppose I'm looking at a rod like this and I apply a load. Right. So the E1, E2 and E3. Correct? Now if I look at the state of stress of this particular beam, which is only under tensile load and is clamped on one end, it would look something like sigma on 1 0 0 0 0 0 and 0 0 0. Correct? This is how the beam would
Yes, sir.
expand. And if I now calculate strain energy distortion, you can quickly realize that this is of the same form as lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, where lambda 1 is sigma 1 1, lambda 2 and lambda 3 are 0. And my strain energy of distortion would be, it is Sorry, I need the formula again. Yeah, my strain energy of distortion would be 1 by, sorry, 1 plus nu upon 3 times sigma 1 1 square plus sigma 2 2 square plus sigma 3 3 square minus of sigma 1 sigma 2 2 sigma 2 2 sigma 3 3 and sigma 3 3 sigma. Nothing but 1 plus nu by 3 times sigma 1 1 square. So I'm assuming isotropic beam. Okay, this is my distortion energy, and this has to be less than 1 plus nu by 3 times sigma y. Now, suppose I give some values, say force is equal to 10 kilonewton, area is 1 centimeter, 1 kilonewton, area is 1 centimeter square. My sigma 1 would be, I can approximate it as F by A, which is 10 to the power 3 upon 10 to the power minus 4, 10 to the power 7 Pascal. And if I'm like for say aluminium mu, I can take 0.3, E I can take, or I'll just assume that the material is steel rather. For steel, nu is 0.3 is 210 GPa, which is 2.1 into 10 to the power 11 Pascal. Right now, sorry, I forgot the value for yield stress. Suppose we'll take, I'll just remove steel. Suppose we take yield stress to be, say, 50 megapascal. That would basically mean that this is 5 into 10 to the power 7 Pascal. And if I calculate my SC distortion for this particular body, it would be nothing but 1.3 upon 3 times 2.1 10 to the power 11 into sigma 1 1 square, which is 10 to the power 14, 10 to the power 11, 10 to the power 14. So this is 10 to the power 3, which is 1000. So 1300 by 6.3. This would be your distortion energy. And it has to be compared with 1 plus nu upon 3 times sigma y square, which should be nothing but 1.3 upon 3 times 2.1 10 to the power 11. Now 5 square is 25 into 10 to the power 14. So we have 1300 into 25 upon 6.3. So as you can see, this value is greater than the strain energy of distortion, which basically tells you that your your beam is safe.
Sir, in the question
Hmm.
he has given the torque applied on the shaft,
Okay.
and he torque and
Hmm.
yield point in tension and the factor of safety. Then how can we find the diameter?
Okay. So suppose you have a T, right? And the shaft is, I'm taking a circular with radius R. You know that your maximum, your tau, theta z. I am taking the cylindrical coordinate system. So this is z, and this plane would have your r and theta. This is r. This is theta. So if you look at your torque expression, it is nothing but T r by j, correct? Tau theta of r theta z. If I write it like this, it is nothing but T r by j. Your T is known, your j is also known because you know your cross section, right? So you can figure out your polar moment of inertia j. It would be a function of r, a function of your radius. You can see that tau theta z would be maximum when small r equals capital R. I draw this as capital R and this as the axis. So when small r equals capital R, your tau theta z would be maximum for the given loading T and for the given geometry. So that tau theta star, I'll write it as T r by j. You know T, you know J, R is unknown because that is what you are saying, right? We have to
Sir,
design the
what is
shaft.
sir, what is
J is
capital
also
R?
unknown, sorry. Go on.
No. So you are saying that the torsion will be maximum when the small.
I'm saying that your shear stress would be maximum on this point. And the reason, and since it's only a torsion loading, right? If I want to plot my sigma, right? Theta z. If I want to write my sigma matrix, it would be not be like tau theta z, tau theta z, 0, right? If you go back to our Morse circle argument, you can see that there is no shear stress in this, like say the r direction. So theta z essentially becomes your plane for drawing the Morse circle. And now your values are tau theta z. Then if I draw my Morse circle, it would look something like this. This is my tau theta z. Okay.
Okay.
This would be my Morse circle, so I can figure out my lambda 1 would be plus tau theta z and my lambda 2 would be minus tau theta z. Now this is here. So J would also be a function of R. I'm probably confused, but for the cylindrical case, I think it's pi r to the power 4 by 2, or it's something of this form. I'll have to look at it. I'm a bit confused at the moment, but what I'm trying to say is that for any point you take on this shaft, right, your stress matrix would always look like this. Then your Morse circle would always look like this, and you can figure out that you have maximum stresses from this equation. You can figure out your maximum stress would always be at the circumferential points. Using this stress matrix, you can also calculate your lambda 1 and lambda 2 to be equal to tau theta z and minus tau theta z each, tau star rather, tau star theta z. And once this is there, you can use your AC distortion equation, which is nothing but 1 plus nu by 3 times lambda 1 square is tau square theta z. To simplify this, I'll rename this as tau square theta z to be some variable a. So it's a square plus lambda 2 square is again a square, lambda 3 square is 0, minus a into minus a, minus a into 0, minus a into 0, right? This is nothing but 1 plus nu by 3 times 3a square. This is your distortion energy, and this should be less than or equal to 1 plus nu by 3 times sigma y square. Now, if you have a factor of safety, you just need to divide it here. If you do not have a factor of safety, you can use this like this, just the way it is. From this, you can determine that, say, your 3a square has to be always less than or equal to sigma y square by n, and a has to be always less or equal to sigma y by root 3. If you are given the material, you know sigma y, you know your factor of safety, you can calculate this entire expression and you can calculate the limit on a, but you know that a is nothing but t into r by j, and j is again a function of r, so this should be something like t upon some function of r, right? So t into function of r should be less than or equal to sigma y by root 3. Now you know t sigma y n, you can go ahead and solve this equation to get a relation in terms of r. So you'll have a limit on r in most cases. maximum radius that your shaft can have.
Sir, I'm really sorry, but
Hmm.
in the distorted energy formula, you have substituted the in the previous slides you have kept the sigma 1 1 square plus sigma 2
Hmm.
2
Hmm.
square,
Hmm.
but here you have substituted it with the directly with the shear stress,
Hmm. Hmm. So that
and
is because, so firstly, no need to apologize. Doubts, everyone has to ask once. So if it gets cleared once, then that's okay. This is our state of stress, right? You agree till this point? This is my
yes,
state of stress,
yes, sir.
right? So if you agree till here, I can also tell you to look at these zeros, right? These are basically your shear stresses on the R plane. So you have no shear stress on your R plane, right? No shear stress on your R plane basically means that your R direction is your principal axis. Now, if your R direction is your principal axis, you can construct a Morse circle.
Okay,
And if I want to construct a Morse circle with these values, I'll first look at the center of my Morse circle. If you remember here,
yes,
we
sir.
talked that the center of the Morse circle is basically sigma 1 1 plus sigma 2 2 by 2 for a stress which is something like sigma 1 1 sigma 2 2 tau 2 1 tau 1 2 0 0 0 0 sigma 3 3. So here the third thing was the principal axis. In our example, the first one is the principal axis, and the center of Morse circle was average of these two, and the radius of Morse circle is, from these expressions you can figure out that the radius is nothing but root of sigma 1 1 minus sigma 2 2 by 2 whole square. So you have a cos 2 theta plus b sin 2 theta. So I am just writing radius as root of a square plus b square plus tau xy whole square. Now I'll go back to our example. In our example, the first entry is the principal axis and the principal plane, and these are the ones that I'm interested in. My center would be 0 plus 0 by 2, 0 plus 0 by 2 comma 0, which is nothing but 0 comma 0, and my radius would be root of 0 minus 0 by 2 whole square plus tau star theta z whole square, which you can realize is nothing but tau star theta z. So if I want to plot Morse circle for this particular, it would look something like, sigma tau, center is at 0, radius is tau square theta z. So I'll just, uh, radius is tau star theta z, yeah, something like this. Okay, this is our Morse circle, and as we also discussed, from Morse circle, wherever the circle intersects the x-axis, your shear stress will be 0, right? At these 2 points, your shear stress would be
Yes,
0.
sir. Yes, sir. So here in mode circle, the radius is
Tau star theta z,
of also 0.
and
So
center is
sigma
0.
So
Yes,
sigma 1 and sigma 2 are you have taken as
plus
yes, sir. I
tau
understand.
star and minus tau star. And I'm just substituting this into SU distortion. Okay?
Okay. Thank you.
Yeah. Cool. Then, do you have any more doubts, or?
No, sir.
Okay, then,
Sir,
thank you for
there
attending.
there are any
Go on.
sir, there are any upcoming sessions on this solid mechanics?
No,
Initial thoughts.
I think this is the last one because you have your exams coming up, right? I think when is your exam?
29 or
20,
30.
29th, right? Yeah. So this is the last one that we have.
Okay.
If you still have any doubts, you can post it, post something on the discussion forum. I usually reply within a day. So
Okay.
yeah. Okay then.
Thank you.
Thank you for attending this session or watching it on YouTube. This is the last session. So if you have still any doubts, you can use the discussion forum. I'll be active there. And all the best for your exams. Thank you.